Welcome back, everybody. This is our second video on using integrals to find volumes. In this video, we're going to start with a function. We're going to rotate it around an axis, in this case the x-axis. And when we do that revolution, it's going to give us some region. And we're going to try to find the volume of that region. Let me show you. So here's my function, and between at least a and b, I want to rotate this line around the x-axis. And when I do that, it's going to produce a solid, and that solid, well, I want to know the volume of the inside. So when I do this, I'm going to just try to copy this, make a reflection, and it goes something like that. Okay, and so let's see, at A, it's going to come down and cut it off here, and at B, it'll come down, let's say cut it off there. And because I did a revolution, well, this picture isn't showing it, so why don't we toss in some sort of revolution, right? It makes a little circle as I go around. Okay, and even on the ends we get that. Here we go. So we get this really nice surface, and we want to know the volume inside that surface. So just as in the last video, we're going to chop this entire region up into little cylinders. Find the volumes of the cylinders, add them up. All right, of course, that's going to involve an integral because we take a limit as they get really, really tiny. That's going to give us an answer. So let's see, just as before, if I extend this out a little bit and make a cylinder, I get some region. And if I know the volume of that, well, of course I know the volume of that. How do I get it? Well, let's see. We saw before we needed to know the height, and we need to know the radius. And the height, well, in the limit was just going to be our dx. So we're going to call that dx. It's really the radius that we care about. And since we're just trying to get from the x-axis up to the function f of x, it's pretty clear what the radius is. It's just, well, if x is the coordinate, the height is f of x. That's the coordinate of this point. And so your radius is actually f of x in this case. Sweet. So if I want to write down the volume of this guy, we know it's going to be pi radius squared. Well, the radius we said was f of x. So f of x squared times the height of the cylinder, which is dx. Okay. Now, of course, we don't just want this one very, very slim cylinder. We want the entire region. And so we're going to integrate all the way across. So the total volume is going to be the integral from, well, let's see. It started at A. It ends at B. And we're just going to add up the volumes of all these cylinders here. So we get pi f of x squared dx. It's just that easy. All right. Now, when I drew this, it wasn't just an arbitrary curve. I actually had one in mind. So I'll spoil it right here. This was actually going to hit at, I believe, at 2, because my f of x was actually x minus 2 quantity squared. All right, so if I actually wanted to know the volume I got by taking this specific function, and actually I guess I should tell you where my a's and b's were. So this a was actually going to be a 1, and this b was going to be a 4. And so in our case, we're integrating 1 to 4 pi f of x. Now what's my f of x? Well, it's x minus 2 quantity squared, and oh my, do we have a little issue. It's not a mathematical issue, it's a human issue. Okay, forgetting about even that 2, but there's this 2 up here, and it looks like I followed the pattern, pi times some function squared. But be very, very careful here. Very often our functions have their own exponents on them. This needs to have an additional square. So we put an additional square there. Okay. Now, at this point, we can see we're going to be able to pull a pi out. I can do a very trivial substitution to make this problem very easy. I'll let you guys handle the details there. But you can check it, and what you should get is 33 pi over 5. Okay, so we're going to do a more complicated example in the next video where we may even go back to our area between curves method and actually put two curves, rotate the area between two curves around an axis. That could be cool. Or maybe we're not going to always have to rotate around the x-axis. What if we wanted to rotate around something else? Turns out philosophy is not going to change, right? All we're going to have to do at each step is work out, okay, what is that radius? Yeah, how far away is our curve from the axis of rotation? Okay, but it'll involve a little thinking. All right, we'll see you next time then.